For this lecture of Data Communications and Network 1 class, this will be lecture 22, chapter 12, part 1, okay, which is about the Internet Protocol. Okay, so this is part 5, Internet and Transport Protocols, okay, chapter 12. What is internet working? Okay, we have heard about the internet. Okay, everyone knows about internet nowadays. What is internet? Internet is come from internet working. Okay, this is a collection of packet switching and broadcast networks. Okay, that are connected together. So this picture is from a text. Okay, so it's kind of older text. So they have the US backbone and the European backbone. Okay, they're supposed to be like Thailand somewhere there, and also so there is this line to Asia, this transatlantic line, something like that. So and then this connected to the regional network. Okay, and the regional network also connected to the LAN, okay, inside of also connected to the LAN, okay, so it's become like smaller and smaller. So at that time, we still have like token bus and token ring in use a lot, and then we have also the Ethernet, okay, LAN. So you can see that there is national network, okay, from the backbone go to national network and then go to the smaller network like LAN, okay. So basically, internet networking means that you connect different network, okay, that have different protocols, okay, different structure, okay, together, and then make the data can be transmitted from the user that connect to different network, okay, to another user in anywhere, okay, in the world, okay, that is connected with the internet. So that is a very interesting concept, okay. Now, what is the glue that holds the internet together, okay? This is made possible by using the Internet Layer Protocol, or IP. Okay, IP comes from Internet Protocol, and IP was designed, okay, with the internet working concept in mind from the beginning. So this one is definitely designed for the internet. Okay. Now let's look at the internet working term. Okay. The first one is communication network. Communication network is just a facility. Okay, that you can you can transfer the data, okay, among the device attached to the network. So it can be a communication network if you can transfer the data between the users that are connected to the network, okay. And internet, as I told you before, there are collections of networks, okay, connected by bridge or routers, okay. And intranet, okay, if you are at Kasetsart, you may have the ku.ac.th that if you want to search inside of the KU, you don't have to log on, okay? Because if you have to log on to go out to the internet outside of the university, but for the network inside of the university, you can search it, okay, without going out, okay, outside of the network. So intranet is just the internet used by a single organization like Kasetsart University that provide the key internet applications, okay? So we have the World Wide Web, and it can also be isolated, maybe self-contained, okay? Or can link to the internet. So if you can have experience that you can get into some of the website, okay? That is like Kasetsart related website, but cannot get in the outside world, okay? That is the intranet. The subnetwork is just look at like like the big thing as the internet, and people think of this as like a single network. Okay, the internet is like a network, so it's like just subnetwork is just some part of the internet. Okay. End system or end users, okay, ES is a device that attached to the network, okay, of the internet that have user applications. So you can have like emails, or you can have like your mobile phone, okay, that can connect to the internet and have a lot of apps, okay. To have the intermediate system, okay? So permit help with the communications between different networks, okay? And bridge is an intermediate system, okay? Connect two LANs together. That usually it use similar LAN protocols, okay? There are some like kind of interchangeably between the bridge and router that people use nowadays, okay? Because but in the actual term, okay, the bridge used for same or similar LAN protocols, but router is the network may not have the similar protocol, okay. So this one is like operate at the router is operate at like the layer 3 of the OSI module, but the bridge is operate at the layer 2 or the data link layer of the OSI module, okay. So it's kind of connect between different networks, okay. But bridge is like operate at the lower layer. You may have heard more of a router nowadays, okay. Now let's look at the internet protocol, the IP operation, okay. Suppose I have a system A and B, okay. A is connected to LAN 1 and B is connected to LAN 2. So I want to send data from station A to station B. Okay, so what can I do? You can see that there is a LAN, A is connected to a LAN, right? And there's a router connected to LAN to the another kind of network, which is wide area network, okay? And this one they use like, for example, frame relay, okay? So frame relay, which is kind of an older protocol, okay, of the wide area network. So frame relay at the other end is also connected to router to LAN 2, okay. So in this case, you can see that you want to exchange the data between users in different LANs, okay, and also through a wide area network, okay. So you have both the LAN and the WAN together, okay. So let's look at the at different layers, okay. So this case we use TCP/IP, okay. So at A we have a physical layer, MAC layer, LLC layer, which is kind of the second layer together, okay. MAC and LLC is kind of the data link layer together. We have the IP, Internet Protocol, which is kind of a network layer, okay. And TCP is a transport layer, okay. So at the system A, okay, the data go to the TCP layer, IP layer, LLC, MAC, and physical layer. And you can see that at time T1, T2, T3, okay. At time T1, you have at time T1, okay, the data goes through the TCP layer, so it have a TCP header, and go to the IP layer, so it have an IP header, okay. So at time T1, the data look like this: IP header, TCP header, and then data. Okay, this is time T1. At time T2, you add LLC header, okay. At time T3, which is at when you pass the max layer, you have the max 1, okay, which is the max of the LAN 1 header, okay, in the front, and also the MAC tailor in the back, okay. Then this is the longest, okay. Then you go to the physical layer, and then you send with a waveform or as a signal, and then you go to the router. What the router do is that it will go up to the internet protocol layer, okay. So so it go to the physical layer, and then MAC. Again, before going to the MAC, it's the same as at time T3, okay. So T3 and T sub 4 is look the same as this frame, and then T sub 5 look like T sub 2, okay, over here, which is the LLC, and then T sub 6 is like go back to the T sub 6 is go back to the first one, okay, which is only IP header, TCP header, and then data. Then the router will just look at the internet protocol and then go to the, so you change, it will change the header, okay, of the data link layer so that it can go through a different network, which in this case is a WAN network, wired network, with the standard of the frame relay, okay? The frame relay has LAPF protocol, LAPF, okay, so LAPF protocol. So the router X, okay, the router X here, it will take the header of the LLC and the MAC out, okay, and it will put the header of LAPF instead. So look at T7, T7 is the first one here, okay, only IP and TCP and then data, and then T8 is here. So you take the first one, IP header, TCP header, and data, this one. T8 is the fourth one. You can see that there is, for T8, okay, you have the frame relay header in front and the frame relay tailer in the back, okay, and then in the middle is just the TCP, IP, and then data. Okay, so you transmit this at the end, okay, of the WAN. Okay, go to the router Y. In this case, T9 and T8 is the same. Okay, still look with the header and tailer of the LAPF protocol. And when you go to T10, okay, at this point the IP protocol will take the header out. Okay, T10 it will take the header out. T10 is the first one again. Okay, take the header out, go back to this form of the first line, and then at T11 the same. Okay, T12 add the header of LLC. Okay, T12 and 313. Okay, so you can see that T12 had the header of LLC, which is a LLC of the LAN 2. Okay, which may use different protocol as the first LAN, and then at T13 add MAC of LAN 2 and the MAC, the tailer header and the tailer of MAC. Okay, go to the physical layer again of the LAN 2, and then go back to the system B and you strip the header out. Okay, at T14, 15, 16 until you get at T16 you get the original IP header, TCP header, and then data again. Okay. So this is how it's connected. So they strip out the header, okay, and then put on the new header. And the router work up to layer 3, okay, of the IP is considered layer 3 of the OSI model because MAC and LLC is in the same layer. Okay, they are the sub layer of the data link layer. Now let's compare the packet switching network architecture and the internet architecture. Okay, when you look at the packet switching network, okay, you have kind of the user is like S1, S2, okay, and then you have the node, okay, like P1, P2, P3, they are the node, and T1, T2, T3, these are the link that is connected between the node inside of the network. Now, if you look at the internet architecture, internet network architecture, you still have user S1 and S2. You can see that you have like router, right? R1, R2, R3, which is kind of the node. The router make the routing decision, okay, on which node to go to, on which network to go to. And in between of the router, okay, there is a network, okay? So the router connect to network, like network 1, N1, N2, N3, okay? So they are connected like this. So if you compare them, the router R1, R2, R3 perform, okay, or work, do the functions similar to the node inside of the network. The P1, P2, P3 is similar to in the packet switching. So what we have studied before, like Dijkstra, Bellman-Ford, flooding, okay, whatever routing algorithm that we done in the packet switching network, it's kind of like we should be able to do in the internet network also, okay? And the network N1, N2, N3 in the internet network, this is just like the link, okay? T1, T2, T3 inside of the packet switching network, okay? So if you consider it like that, you can apply the routing algorithm, okay, to to do the routing for the internet network too. Okay, again, T1, T2, T3, the link is just like the network 1, 2, 3. Okay. Now the design issues, okay, let's look at the design issues for the internet. Okay, the first one is routing. The second one is datagram lifetime, fragmentation and reassembly, error control, and flow control. Now for the routing, as we have just looked about, just see the picture before. Okay, as I say, you can do many kind of routing. We can have a lookup table. Okay, in this case, if you have like use the least cost algorithm, for example, and you have the routing table already, so the end users of the routers, okay, have the routing table. So you put, okay, the best way to go from this LAN to another network is this way. Go to this router and that router, something like that. This can also be static or dynamic. Okay, if it's like the virtual circuit switching, similar to that. Okay, it's kind of static. But it's dynamic is kind of like the datagram in the packet switching. But in this case, it's in the upper scale. Okay, increase the scale. Okay, to be like router of different network. Okay, whether they keep updating the condition. Okay, to make a new decisions of which way to go. If there is any suggestion, congestion in some of the paths, or some of the path is not working, something like that, and you should go another way, something like that. But if it's static, it's like you always fix to go from, if you want to go from this LAN to another LAN, okay, you always go past this router and then that router, so that is static. The second one is source routing. Okay, this is an option. This is the case that I will talk about. That it source is the one who set the whole route. Okay, for a datagram to send to. In this case, we may set it for security purpose or priority purpose. For security, it's like when you want to use the infrastructure of the company that or the military, okay, that you trust. Okay, if you have like sending a secret, you don't want it to go to like fastest way or cheapest way, but you want it to pass only on the military network, something like that. Okay, or priority purpose, like this one have to go like first. Okay, have to arrive. It's urgent message, something like that. Okay. Now the datagram lifetime. What is the datagram lifetime? It's about how long it will stay inside of the network. Okay, because if you don't set the lifetime, it will just stay inside of the network indefinitely. Okay, so it just will go from this one, go to that one, go to this one. Okay, it will never die. Okay, so if you have a lot of people input the data in, okay, and the data will not, will live forever. Okay, it will get congested and no one can send anything. Okay, so in the IP field, in the IP protocol, in the header, there will be a field called time to live field. And if the time to live is used up, then you discard that datagram. Okay, and you can also send an easy way, okay, to set the time, okay, for the packet to still have stay inside of the network is you can use hop count or time count. Okay, so hop count is like if you go 4 hop or if you go 10 hop, okay, and you -1 for every hop. When the hop count is equal to 0, you discard the packet. This is similar to what we done in the flooding. Okay, in the example in the flooding techniques. Another one is a time count, like you stay for like 5 minutes, for example, or 10 minutes. If not, just discard it. The third issue is the fragmentation and reassembly. For this one, okay, because the message can be big, the datagram can be big, okay, it can be too big to transmit through some of the networks, like the ATM network, okay, asynchronous transfer mode, that you have the cell that is very small, only 53 bytes, okay, and the data is only 48 bytes per cell. Okay, so you send from another network. Okay, usually it's bigger than ATM, so you have to kind of fragment it. Okay, when you go from different networks, they have different constraints because you cannot. There are many protocols, okay, that is already exist, okay, but the internet have to be able to go through all of the network with different protocol to arrive at the destination. Okay, so you can have different packet size, and so you can fragment it into a smaller section, smaller box, okay, to get into the network, okay, with the limited length of network in the protocol, okay, and so you also need the assembly, okay, at the end system, because if you have like small portion and you have to put it into the whole box or the whole packet, okay, original packet, so you can do it at the destination, okay. Now, if you look at this, you can see that you have the original, okay, IP datagram, okay, you have TCP header, and then the IP header, okay, IP header for 20 octets or 20 bytes, TCP header for 20 bytes, and then TCP payload, okay, this is 384 octets or 284 bytes, okay. So for the original IP datagram is the whole thing here, the blue and the gray, okay, box, okay. IP datagram have the data length of 404 octets, okay, because the TCP header and the TCP payload become the data or the information field, okay, the payload of the IP datagram, okay. So the gray is the data field of the IP datagram, consists of the data of 404 octets, okay. At first, okay, there is no segmentation, so segment offset is 0, more is 0 because only one packet, okay. Then you fragment it, okay, because like for example, it's too big. When you fragment it into two smaller datagram, okay, both of them has to have the IP header. You can see the blue color here. You have both of the segments, okay, have to have the IP header of 20 bytes, okay. Then you have so for what I was talking about, the ATM, they will use the ATM adaptation layer instead of this, okay, because this one has too long of the header, okay. Anyway, you have in the first segment, okay, the data length is 208 octets, okay, because you divide the data, okay, into the first part and the second part, okay. The segmentation offset, okay, segment offset is 0 because this is the first segment, okay, so there is no offset. More is 1, which means that there is more packet coming, okay. The more can be only 0 and 1, okay. Cannot be like 10 more packet or 20 more packet coming, more is 20. It's not like that, okay. More is 1 means that this is not the last segment. Okay. And this is the second segment. You have again the IP header, and then the last of the payload, okay. In this case, the data length is 196 octets, okay. Segment offset is 26 of the 64-bit units, okay. So instead of saying offset by 10 bits or 2,000 bits or something, okay, they will look at it in terms of the 64-bit units, which is 8 bytes, okay, because 1 byte is 8 bits, right? 64-bit is 8 bytes, so it's 26 times of the 8 bytes unit, okay. More equal to 0, okay. The 26 of the 8 bytes unit is 208 bytes or 208 octets, okay, which is just this, okay. The first one has a data length of 208, right? Because so it's offset by 208. So this one has a segmentation offset. It's basically 208 bytes, okay? But it will show it as 26 of the 64-bit units. This is segment fragmentation examples. The next one is the error control, okay? For the error control, in the IP, okay, we don't guarantee any delivery of the message, okay. So the router will try, okay, to tell the source if the packet is discarded but no guarantee, okay? It may or may not tell the source, okay? And the source, but if the source knows that a packet is discarded, it may change the transmission strategy. Maybe it will wait for a little bit, okay, before transmitting the next, the packet that has been discarded, retransmit it, okay? Because if the packet is discarded, it may be because there's congestion inside of the network, okay? So maybe you should wait. And in this case, you need a datagram identification or the ID of the datagram or the packet, okay? So that you know which packet is discarded and then you need to transmit. If the feedback, okay, to the source is needed, IP will use the Internet Control Message Protocol, or ICMP. This one is a protocol that provides the feedback about the problems, okay, in the internet. So this is kind of a special protocol, okay, to do the feedback. The next topic that we should concern about is the flow control, okay. For internet, it is connectionless system. Connectionless system means that you don't make a connection like from the source to the destination first before you transmit, okay. Like the connection oriented is kind of like the circuit switching, that you make a switching of like every part, okay, in between until you have a link, okay, a direct path at the end from the sender to the destination. But in the internet case, you cannot do that, okay? There's pass through too many networks, okay? You cannot control how many networks it has to go through, and also the protocol. So it is a connectionless system. So we cannot do much of the control, flow control, okay? But we can do a little bit. For example, if it's like congested, okay, inside of the network, there may be some use ICMP, okay, to tell the source to slow down the data rate of the transmitted data rate or to of the flow that the source sent out, okay, so that there will be no more like it will ease the congestion inside of the network, okay. So the next one. The next topic we talked about is the TCP/IP. This is a protocol suite that we use together, okay? So this is Transmission Control Protocol / Internet Protocol, okay? As I told you before, the IP is connectionless, okay? So it's a connectionless datagram protocol, and it's also unreliable. Unreliable means that it has no guarantee, okay? It will just its best to get the data, okay, or your datagram pass through the network, okay, to reach the destination, but it will, it have no guarantee that it will have to arrive 100%, okay. So this is kind of a best effort delivery service, okay. Do it at best as it can, but no guarantee. So this is kind of an unregistered mail, okay. Post office does its best, okay, and use. Normally, okay, the mail is not lost, okay. But anyway, there's no guarantee. If it's lost, you don't know what happened, okay. So if since IP is an unreliable protocol, no guarantee, and if you want to have more reliable, okay, and reliable transmission, you have to use it with a reliable protocol. Another protocol to provide reliability, which is the TCP. That's why the TCP and IP are almost always used together, okay? They are commonly used together, okay? Now, the communication step in the internet, okay, is that the transport layer, TCP is in the transport layer and it's higher layer than the IP. So transport layer take the data stream, break it into datagram, okay? And then each of the datagram is transmitted through the internet, okay? And as I told you before, if it's too long, okay, and too long to get into some of the network, okay, it will be fragmented into smaller units, okay? And when all of the units arrive at the destination, they will reassemble, okay, based on the fragment offset, okay, and the identification. Okay. And then the the datagram, okay, will go to the transport layer of the destination, because again, I told you the transport layer is in the higher layer than the IP, the network layer, right? So you just go back to the transport layer, and the transport layer reassembles the datagrams, okay, into the stream, the data stream, to send to the user again. Now, TCP/IP is a set of protocols, okay, or which sometimes we call it protocol suite, okay, define how all transmissions are exchanged across the internet, and this is a very popular protocol suite, okay. If we compare, actually in the chapter 1, I think we compare a little bit already about the TCP/IP and the OSI open system interconnection, which you may remember that OSI is kind of a model, like conceptual model, okay, but no one uses it, okay. It's not used commercially in practice, okay. So TCP/IP are the one that is the kind of a de facto standard, which means that like people are using it, okay. So it's kind of become sort of a standard because everyone is using it, okay. So this is a dominant commercial architecture and developed before OSI. So when OSI come out, but people have used TCP/IP already, no one wants to change, okay. It consists of 5 layers, the application layers, TCP/IP network layer, okay, and the physical, okay, physical we don't see here. And the application layers of the TCP equal to the 3 highest layers, okay, of the OSI. So in the TCP layer, we call the block of data as a TCP segment, okay? But in the IP layer, in the internet layer, we call this one IP datagram. And the network layer, we call it network level packet. Okay, so it's different name for a box of bits, okay, of kind of a packet. At different layers have different names, okay? Segment, TCP segment, IP datagram, network level packet, okay. Now the TCP/IP protocol suite, okay, have 2 of the transport level protocol. The first one is called TCP, and the second one is called UDP, okay. So it's not only TCP that is used. TCP is a connection oriented, which means that you know which way to go, okay. You have connection, okay, before you transmit. And this is, so since most of the applications want reliably delivery, okay, so TCP is more widely used than the UDP because it provides connection oriented and reliable transmission, okay. But if you want it to be fast, okay, and you don't care much about reliability and security, you can use another protocol that is called UDP, okay. UDP is connectionless, so it's like you transmit like a datagram, okay, one by one. This one, UDP, is simpler than TCP and is used to transmit quickly, okay, without don't have like much need for the reliability and security as the speed, okay. So there's a need for speed more. So TCP, as I say, that is provide reliable communication between pairs of users, okay. We call the users a TCP user process. So it provides like reliable communication between 2 processes, okay, across reliable and unreliable networks, okay, such as in the internet. So even though the network is unreliable, TCP can provide delivery that is reliable. So it's very popular, okay. The TCP segment, and also this is needed because in the internet, there are many networks. So some network may be reliable, some network may not be reliable, okay. So we rely on the TCP protocol, okay, to help us make a delivery that is reliable. Now, the TCP segment has TCP header that consists of 20 to 60 bytes, okay, and then the user data. the TCP header format, okay, which has a 20 byte minimum, okay, consists of source port, okay, and destination port. For each of the line, okay, is 32 bits, okay. 32 bits means that there are 4 bytes, okay, because 1 byte is 8 bits, right? So 4 bytes is 32 bits. So you have source port of 16 bits, destination port of 16 bits, okay. 32 bit sequence number, 32 bits acknowledgement number, okay. You have data offset, you have reserve, and some of the urgent, acknowledge, push, reset, finish, okay, the special bit, okay, flag, like to tell you that this is reset or push or urgent, something like that. And you have the window, okay, window, this is kind of a sliding window techniques, okay, that we will talk about later. You have the checksum, which is source of the error correcting code, the priority check bits, okay. You have the urgent pointer, and then you have options, okay, and padding that you can put in there. The sequence number, okay, indicate the number of the first data byte, okay. So this indicate in terms of byte, okay. So this is the byte of this TCP segment, okay. So first data byte of the TCP segment, okay, not the number of the TCP segment. So kind of not the frame number, but the byte number, okay. For example, okay, this should be header, okay, TCP header over here. You have TCP segment, okay, and the sequence number is 3001, okay, in the TCP header because the first segment, because this segment, the first data byte is byte number 3001 to the last one is 6008, okay. The next one start at 6009, so the sequence number is 6009, okay. So you can think of the sequence number and acknowledgement number as the send sequence number and receive sequence number, as we have done in the data link layer protocol, HDLC, okay. However, in the TCP, the number will refer to the number of bytes, okay, not the number of segment or frame, okay, as we have done before. The window size, okay, in the header we use for flow control, okay, and you can reduce the window size, okay, but prior permission cannot be taken back, which means that if you allow to send up to what byte, okay, you cannot. So for example, I allow to send up to byte number 10,000, and then another minute I say, oh, I allow up to only byte number 8,000. Okay, this is not possible. Okay, how to set the window size, how to use the window size, and how to understand why the prior permission cannot be taken back. Okay, we will talk about this in the next video. Okay, so this is the end of this video. Thank you.